In this example, we look at the differential equation dp dt is 1 minus p times p. So this has some flavor of the explosion equation in that we have a product, but it also might remind us of a rumor spreading differential equation that we found earlier, where we had a k, a p, and an n minus p. We have a p, something minus p. This is actually a simplified equation here of the rumor spreading. And this logistic equation is quite famous. It's used a lot in biology as well as epidemiology for studying how diseases get spread through populations. We're going to look at it simply here as a separation of variables example, though. So we do our usual thing of separating and integrating. This time, all the p's have to go with the dp. So we have 1 minus p, p, dp. The dt comes up, and then we integrate both sides. The right-hand side, straightforward. It's just a t plus a constant. The left-hand side is more complicated, though, but fortunately, we have a technique that works on that. If we look at the denominator, it's a product of two terms, and that's exactly what partial fractions as a technique is designed to handle. So what we're going to do is do a little aside with the partial fraction decomposition and write out our expression 1 over 1 minus p times p can be broken down into one constant over the 1 minus p part and another constant over the p itself. So the two linear terms. Then we cross multiply, get a common denominator. This is missing a p, so I'll have a times p. And in the other term, we'll have b times 1 minus p. These would all be over the same common denominator, but that doesn't really play a role in the calculations. But that's how we get to this second expression here. Ignore those, ignore those. So now we equate the numerators, and these have to be true for all p. If they're equal for all p, then what we can do is plug in some interesting values for p. In particular, if we make p 0, then the left-hand side is just 1. We have 0 times a, and we have b times 1, so b would be 1. We also have, as an easy case, if p was equal to plus 1, this would go to 0. And under that scenario, we would have a times 1, and so we'd have a is equal to 1 as well. What that lets us do is isolate the value for a and b and rewrite our complicated integral, which is a multiplication or a product, as a sum instead, and it's way easier to integrate sums. So our next step is the partial fraction decomposition of what we started with. A was 1, b was 1. We have that new integral still equaling the same right-hand side we had a second ago. But the nice thing is we can actually evaluate that new integral that we have on the left. Both of these terms give us ln values. Be a little bit careful here. This will give us a -1 because of the negative p. And we also have ln of p equals t plus a constant. Separate those, and we proceed from there. Our goal from here is to isolate for p. Now this is the most complicated scenario we've seen. We actually could just stop and say there's an implicit relationship, but if we're careful we can actually get down to p equals. So let's try that. Just being careful with each step. We're going to bring this -1 up, multiply through by it. That'll give us negative t minus c. Now we need to get into the lns, but they're two separate lns right now. Fortunately, there's a rule that says if we have a subtraction or a difference of lns, what we can do is divide inside the ln. And in that scenario, what we can do is tidy up a little bit further and have ln of 1 over p minus 1. Now that's going to be very, very helpful because it means we can isolate for p. There's only one p left at this point, and again, that's what we're looking for, p equals. So we should be able to isolate it from here on in. We'll bring this to the next page and continue. With this expression, we want to isolate p. That means getting rid of the log or the ln. So we exponentiate both sides. E to the ln goes away. And on this side, we have e to the negative t times e to the negative c. We have our absolute values. We'd like to get rid of those. So we're going to invent a new variable. We'll call it a. E to the negative c is just some bigger constant that we don't know. We'll let that be mainly what a is, but we're also going to have a plus or minus as needed to get rid of the absolute value signs. And that leaves us with 1 over p minus 1 equals a e to the minus t. So this term here turns into a, and we have the e to the negative t. And now we're in fantastic shape for solving. 1 over p is a e to the minus t plus 1. Bring the p up, all this down. 1 over 1 plus a e to the minus t equals p. And that should be our general solution. Now again, that was a fairly complicated process to get to it. I think it's probably a good cautionary exercise to verify that this solution is correct. Again, it shouldn't be that hard to sub it into the differential equation and verify that we actually do get 1 minus p times p. We'll do that in the next page just to confirm our answer. There's our solution, and the left-hand side is dp dt. Now this is a fairly complicated function to differentiate, but it's essentially this to the power negative 1. So we're going to have negative 1, 1 plus a e to the negative 2 to the negative 2 times the derivative of the inside, which would be a e to the negative t times the derivative inside of that, which is negative 1. We can tidy that up a little bit. There's double negatives going around, so we'd have 1. We'd have an a e to the negative t on top, and a 1 plus a e to the negative t all squared on the bottom. Compare that with the right-hand side, which is simply our function times 1 minus itself. And that we can work through. It's going to be a little bit involved just to get the right form for it. But there's our 1 minus p and our p. With those two expressions there, hopefully we can cancel things out and get this. The easiest way, I think, is the common denominator. Then we'll have the denominator squared that we need. So it'd have 1 plus a e to the minus t. That's the 1. Minus 1 all over 1 plus a e to the minus t. And our p again is there. What we do get is the denominator of 1 plus a e to the negative t squared. That's perfect. And in the numerator, we have our a e to the negative t with the 1 and minus 1 canceling. Once again, we do have left-hand side equals right-hand side, so we've confirmed that our solution is in fact correct. And that's a demonstration, again, of a slightly more complex differential equation in the sense that the separating and integrating was more involved. But at the end of the day, the process was identical. We separated, we integrated, and then we just used whatever integration skills we needed and whatever solving skills we needed to isolate for the solution we were interested in. Here, p as a function of time.